Cheerful greetings, everybody. Welcome to the sequences and series part of proof by induction. So this question is prove that the sum of I, where I goes from 1 all the way to n, is equal to n times n plus 1 divided by 2, where n is an element of the positive integers. This sign z is used for integers, and the plus at the top just means it's positive integers. So, before I move on to proof by induction, I am just going to clear what this sign actually means. And if you already know what the summation sign means, you can skip the video ahead and continue with the part where I explain proof by induction. So, moving on to the summation sign. This sign is called sigma, or the summation sign, and next to it we have an equation. And what we know about this equation is that this I here, it starts from being 1 and it keeps on increasing and goes until the number 5. So what we have to do here is, when our I is 1, we have to substitute the value of I in our equation. So for example, right now the value of I is 1. So we are going to have 2 times 1 plus 3. Then our I increases to the value of 2, and then we have 2 times 2 plus 3. And so on and so forth. Now that we've already substituted all the value of I, because it's summation sign, it mainly means we have to add all of these terms together and then obtain the answer. So this is going to give us 2 plus 3 is equal to 5. This will give us 4 plus 3, 7. And now that we have found the answers, we can add all of these, and the answer we get is 45. So this is equal to 45. The summation sign, although it looks quite daunting, but it's actually quite simple, as you can see here. It mainly means you have to add all of these terms up. So now that we've covered it, let's move back to the question. Proof by induction, the very first step, as I've explained before, is to show that the equation works for n equals 1 or 2 or any integer which you wish to take. What you have to do in sequences and series questions is that you have to prove that the left hand side of the equation is equal to the right hand side of the equation. So, for n equals 1, we're going to have the sum I equals 1 all the way to 1, and then we have I, and we're already giving the value of I as 1, which gives us 1. So this is the left hand side of the equation. Now, the right hand side of the equation, our n is 1, so I'm going to substitute the values. That's 1 times 1 plus 1 divided by 2. That is 2 divided by 2, which gives us 1. And 1 is equal to 1, so it works. Step number 2. We have to assume that the proposition holds true for n equals k. What that means is that the sum of I equals 1 all the way to k of I equals k times k plus 1 divided by 2. Now, usually, as I said before, you have to show that the value, the k plus ith value, is also true, and that is what we have to show. So what you can do here is that whenever you have to show something, you know that your end result should be k plus 1 times k plus 1 plus 1 divided by 2. That means k plus 1 times k plus 2 divided by 2. This is what you are aiming for. So in the third step, when we do our main step of induction, you have to manipulate the equation in such a way that you end up getting this result right here. So let's move on to the third step. I'm going to write here the summation of I equals 1 to k plus 1 of I. Now, be careful here. You cannot just say that it equals k plus 1 times k plus 1 plus 1 divided by 2. That is wrong. What you have to rather do is manipulate this equation And when you manipulate, then you have to make it equal to this sign. What you need to know is that this is the same as sum of I equals 1 to k of I plus another value of I. Why is it the same? Let's use an example to show why it's the same. So, for example, if I have sum of I equals 1 all the way to 3 and the value is I. This, I know the value of I is 1, so I have 1. Then the value of I increases to 2, so the other value is 2. And then the value of I increases to 3, so then I have the value of 3. And that gives me 1 plus 2 plus 3. Let's ignore the equal sign at the moment. Now if I ask you to find the value of I equals 1 all the way to 3 plus 1, which is the same as the value of I equals 1 to 4, you can say that this is the same as 1 plus 2 plus 3, 1 plus 2 plus 3, plus another value of I, which is 4 at the moment, plus the value of I at the k plus 1th position, which is 4. In a similar way, this equation can be written as the value of I all the way to k of I plus the k plus ith value of I. This equals k times k plus 1 divided by 2. Why? Because this is what we assumed from our second part. We assumed that the value of I equals 1 all the way to k is k times k plus 1 divided by 2, which is what I've written here. Plus, now this value of I, as I said before, is the k plus ith value of I. So instead of writing I, I'm going to write k plus 1. That being said, let us now move on to solving the equation. I can take the k plus 1 as a common factor, so I have k plus 1 times k plus 2 divided by 2. And that is exactly what we wanted to reach here. As you can see, it is fairly simple and similar to the divisibility questions. The things to notice here is that you have to show in the first step that the left hand side equals the right hand side, and then you make an assumption, and in the third step you have to remember that the sum of I from 1 all the way to k plus 1 is the same as the sum of I to the value of k plus the k plus 1th value of I. And that's it. I hope it was helpful, and thank you so much for watching. I wish you all a very productive day ahead.